All right, so in this chapter, this is a chapter that is only for HL, so SLs, if you're here, you don't need to be, so you can stop this video right now and wait until the next chapter. But for HLs, we're going to talk about a lot more complicated integration problems. The first two that I want to talk about are two special things to look for when you have an integral you're trying to evaluate. But let's go back to when we were talking about the derivatives of the inverse trigonometric functions. If you remember, the derivative of the arcsine of x was something specific. But when I change it to the arcsine of x over a, this is what I get right here, 1 over a squared minus x squared. So I'm just going to show you how I get that. So if I have that y equals the arcsine of x over a, then I can rearrange that by taking the sine of both sides and then multiplying both sides by a, and I will get x equals a times the sine of y. And so now what I'm going to do is I'm going to take the derivative of x with respect to y. So I'm going to treat x like it's the dependent variable and y like it's the independent variable, so it's kind of the opposite. So that means that dx dy is a times the cosine of y. And if I replace cosine of y, remember sine squared plus cosine squared equals 1. So I can replace the cosine of y with the square root of 1 minus sine squared y, just by using that identity. The only reason I do that is so that I can make another substitution later on. So if I have a times that square root, that's the same thing as having the square root of a squared times that root. So I'm going to multiply the square root of a squared times the square root of 1 minus sine squared, and I'm going to get the square root of a squared minus a squared sine squared y. All right, and the reason I do that is because if I look at the second thing under the square root, that is the same thing as what I set x equal to, only squared. So I'm going to change that second term to just x squared. So dx dy is the square root of a squared minus x squared. Now this might seem like a cheating thing to do, but if I want to figure out what dy dx is, I just flip it upside down. So instead of being root a squared minus x squared over 1, it is now 1 over a squared minus x squared, or 1 over square root of a squared minus x squared. All right, and what that means is if I integrate that function, then I will get right back to the function I started with, arcsine of x over a plus some constant that may or may not be there. All right. And the second one that I want to look at is arctan, only because arccosine looks a lot like arcsine except that it's negative, so I'm not even going to think about that. So I'm going to look at arctangent. The derivative of arctangent of x over a is a over x squared plus a squared, and I'm going to show you why that's the case again using the same trick that I used in the last one. Instead of saying that y is the arctan of x over a, I'm going to take the tangent of both sides and multiply both sides by a. And I'll get that x equals a times the tangent of y. All right. And so if I take the derivative of x with respect to y, then I get a times the derivative of tangent, which is secant squared. And then I'm going to make another substitution based on another identity I know, and that is that the tangent squared plus 1 equals the secant squared. Or, in this case, the secant squared equals tangent squared plus 1. All right. And I distribute the a again, so it becomes a times tangent squared plus a. But remember, the last time I was able to make something so that I could substitute x back in. And I almost have that here. I'm just missing an a. So what I do is I multiply both of these by a, and then I divide by a, which is like multiplying by 1. So I get a squared times the tangent squared of y plus a squared all over a. And so just like before, this a squared tangent squared y is just what I set x equal to, except it's being squared. So this is the same thing as x squared. So I make that substitution, and dx dy is x squared plus a squared all over a. So if I flip that upside down, I get dy dx. And so the opposite must be true. If I integrate this function, I will get back to the arctangent of x over a plus c. So Note the similarities in those two functions, note the differences in those two functions so that you know which one you're solving for. If I look at this one, for example, I notice that there's a square root on the bottom and the two things under the square root are being subtracted. So that leads me to believe that I should be using arcsine. It doesn't look exactly like arcsine because there's a number sitting in front of the x squared and there's a number on top. So I'm going to take care of both of those things. I'm going to factor the 9 out of the top, and I'm going to factor a root 4 out of the bottom, and that's what I'm left with. And since all of this is just a constant, I can pull it out front so that there's a 9 over 2 sitting out front, and then there's something that looks a lot more familiar in the integral. And now that I know what the rule is, I know that this is the integral of this function is just arcsine of x over 3. And I keep the 9 over 2 out front, and I add a plus c at the end. Okay. And so let's now do an example where I will more than likely get arctangent. So I have this example here. It looks nice, except I've got this 7 on the top, and I've got a 5 in front of the x squared. So same thing. I'm going to factor a 7 out of the top and a 5 out of the bottom, and I'm left with something that looks a little more familiar. So this is 7/5 times the arctangent of x over 2 plus c. All right, and we'll do more examples tomorrow. If you have questions, let me know, and I'll see you tomorrow.